elementary. That's just nonsensical, cartoonish stuff that has nothing to do with the level of work we're going to. We're actually going to cover a lot in detail about how general relativity works. But elementary is essentially what you would talk about to be I suppose we would say a one-year course, right? It's certainly a one-semester course would be elementary. But a one-year course is, I think, more the idea of where we're headed, a total one-year course. I don't know how long it'll take us to get there, actually, but I'm thinking if you're in a regular university, we'd be thinking about a one-year course. I'd like to get into some topics that are certainly intermediate, but we are going to begin with the elementary notions. The thing is we've actually covered a lot of the elementary notions in many ways when we did the What is a Tensor series of lectures. So organizing the class and getting the prerequisites down, that's really the goal of this first lesson. So let's talk about the prerequisites. If you're here, you have done What is a Tensor. You have done the What is a Tensor playlist probably through lesson 21. There's 40 lessons in this playlist. You don't need them all to get started with this class. However, up to 21, I think, is logical. That is, pretty much once I get on this massive 20-lesson diversion into forms in that playlist, you can stop there for now, right? Well, ultimately, we will have to come back to it and apply it. If we're going to go anywhere near the upper edge of elementary into intermediate, you will definitely need to work with forms. But in the beginning, not so much. So we can skip that part. But also the part that I want everybody to have is what is a manifold, right? That playlist up to about 11, right? So that would be the definition of a manifold. Now, the reason we do these things is general relativity is constructed from tensors, right? Tensors is the mathematical objects which we use to construct the laws of general relativity. Manifolds are the mathematical objects we use to model space-time. So these model space-time, and these express the laws, right? So you need both, right? So a lot of the elementary GR is already done once you hit these two prerequisites. But it is important. I'm going to presume that you know these prerequisites. Now, it's not like we're not going to go back and discuss them again. We will, especially when we have to describe. We know what tensors are, but I have to describe each tensor that's important to this theory of general relativity. We haven't done that yet. Same with manifolds. We know how manifolds work. We understand the topology of manifolds, the elementary structure, the nature of a differentiable manifold. But we have to show a specific manifold for space-time, say, around a star. And that's what we'll do. We'll do this Schwarzschild solution in great detail. Okay, so these are the prerequisites for this class. Now, ideally, you've already read some special relativity, right? Special relativity is not very difficult compared to this subject. However, different students have different exposure to special relativity, and those exposures vary widely in how deep and how complete they are. So I'm going to give a small one of the first lessons in this course is going to cover some of the ideas of special relativity that you need to have taken away from that. I'm not going to reteach special relativity, however, but I'm going to give you some ideas that if you don't fully understand, you need to kind of go back and bone up on it, right? They are important, right? Remember, general relativity is truly general, and it's generalizing something that's special. So you might think that the way actually learn this first and then that. And the reason is because this is flat space and this is any space, right? Or any space-time, I should say. And that's just how science proceeds, right? Science proceeds by understanding what's right in front of us. And what's right in front of us is essentially flat space. Now, that's not true. Of course, we live in a field of gravity, and we know that gravity represents a curvature of space-time, so that the correct way to model the Earth with gravity is actually, ironically, general relativity. However, you can just like with objects moving through space on the Earth that they seem to stop and slow down due to friction, you first kind of understand this weird special world you're living in, and then you abstractify it and you say, wait a minute, without friction, things would just move forever. It took a long time for philosophers and scientists to figure that out. In fact, probably entirely philosophers at that point. So we're kind of dealing with the same thing. We create a flat space world, the one we live in, because it makes sense. It's easiest to understand mathematically, and there's no hint of any of this. But once we understand this, and with a few other additions, that's where we generalize. We generalize the special case to any case instead of understanding the general case and saying, oh, let's just do a special example of it. Okay? So the point being that we learn special relativity first, and we will have to review some of those concepts probably in the first lesson. So these are the prerequisites. If you have to be comfortable with special relativity, and this playlist up to 21, and this playlist up to 11. Okay, now the other one. GR books. And this is a very hard question because there's so many, and the stuff has been around since the good books have been around since the 70s, and books about it have been around since 1920. So there's the advanced books,